Hello and welcome to a very special edition of Happy Maths Hour. We are celebrating Maths Week Ireland. Now normally I go in the form of bubbles in my orange outfit to Ireland and travel all around the island of Ireland. It's a pan-Irish Maths Week. And so a big shout out to all you wonderful people that I normally get to go and see in person and haven't seen you. This is the second year running I haven't seen you, and I really, really hope I get to see you next year. A big thank you to Kelmas, to Science Foundation Ireland, to Owen, Sheila, and the Maths Week Ireland team. And thank you for inviting us to be part of Maths Week Ireland in a small way. And we'll do Happy Maths Hour every year for Maths Week Ireland if you'll have us. And I look forward to seeing you next year. I have here a wonderful, wonderful Toni Beardon. Now, if you have heard of the Enrich website, Toni Beardon was the founder and chair originally of the Enrich website. Since she retired from Enrich, she has done amazing things in Africa. She's created an organization there that trains teachers, that provides professional development for teachers. And I'm going to let Toni tell you all about it. Go ahead, Toni.
Well, what can I say? It's a charity. We work mainly in South Africa, but also in East Africa. And we have a lot of volunteers all around the world who get involved, either going to Africa or doing it online. And we work with teachers, particularly teachers in the most disadvantaged communities. The idea, our hope, is that if children get a better education, however disadvantaged they start in life, having a good education will enable them to have better life chances, and so we empower the teachers. Okay, so it's reptiles today. So Caroline and I do this Happy Maths Hour.
Yeah, they're a bit scary. We do. And Toni said it was reptiles. I'm a bit scared of reptiles.
Big dragons, yes, no. I'm very much in favor of dragons because I was born in the year of the dragon. Okay, so what is a reptile? Well, a reptile is a shape, okay, that it can be used to tile the plane. So you can, as you see here, you've got 4 reptiles fitting together, a blue, red, yellow, and green reptile. And this reptile we call the Sphinx because it looks, well, you can imagine it a bit like the famous Sphinx. And a reptile is so you can dissect it into smaller identical copies, but you can also build it outwards, adding more copies to make a bigger one, an enlargement of that same shape.
Like a fractal.
It is, and we're going to show how similar to a fractal. In fact, some of these reptiles are fractals, others are not. And the Sphinx can be made up of 4 smaller copies of itself. So it's called a rep 4. So sometimes they can be made up of 2 copies or 9 copies or different numbers of copies. This one is a rep 4.
So that shape that looks like a bit like the Sphinx, hence it's called the Sphinx. I can see a blue, a red, a yellow, and a green, and each one of those is basically a smaller Sphinx. So it's a rep 4 because it's made up of 4 copies of itself. Oh yes, the grey one on top is an example of one of the copies. Nice one.
Yes, and you can have a lot of fun with this, and we'll give you some things you can try for yourself. So all you really need is a pencil and paper. And you can do some doodling if you like, and you can be very creative.
I've got my coloured pens, I've got my square paper, although it's even better than square paper is that with the triangular dots. What's that called, Toni?
That's called isometric paper, yes. If you've got that, that's even better. But you don't even need a grid. You can just do it on ordinary paper. So that's what a reptile is.
Right.
Now watch this. Now here we have a hexagon, and this is filling the plane with smaller hexagons. So here we can see red, green, yellow, and blue hexagons. And much of the content I've got here, including this a GIF, comes from an article on Wikipedia. So thanks to Wikipedia, you can see.
So in fact, all you need to do is search for reptile there, isn't it? That would work. That would do the job, wouldn't it? Let's have a look.
We're very used to seeing tessellations or tilings, if you want to call them tilings. There is a mathematical difference, but we won't go into that. We're very used to seeing tilings with hexagons that are all the same size, like a honeycomb. But not this sort of thing where we've got smaller and smaller ones. So as you see, this could, imagine this going on forever. It actually stops after, well, there's a pause, but we can imagine it stopping after 4, 1, 2, 3, 4 different colored copies, but it could go on and on and on forever. So that is a reptile, and that's one with a regular hexagon. Now here,
okay, well that's, oh wait, this is, we've seen this before.
Yes. Now here I've shown you 4 tessellations here with different shapes. The one on the top left is one I absolutely love, the sun and the moon. And if you concentrate on that, you can see grey birds. Can you see grey birds? Concentrate on the grey birds.
I can see the grey birds, they're flying.
And the sun is in the background. Now change your attention to the white birds with the night sky in the background.
I'm just going to make this, I'm going to disappear us for a moment and make it the whole screen to make it a little bit bigger. So you've got the grey birds, and then you've got the white sky. Oh, you can see a sun right in the center there. It's like red sun, isn't it? With yellow around it. And the rays of the sun are the red and the background is white. And those give you the silhouette of the other birds. Okay, I can see that.
So if you concentrate hard on the white birds, you'll see some of them in the middle are yellow and orange, red and orange. But you can see the night sky behind those. That's beautiful. That's an Escher artwork. Now,
do you think that's the moon, the white that's in the middle there, and stars?
Yes,
I can see the moon and stars now that I look at it.
Yes, I just love that one.
Escher's amazing.
I've got a print of that on the wall in my sitting room. Now then, the other one has got lizards. We won't call them reptiles. They're just lizards, but these lizards are green, yellow and red. And you can see they're all the same, whereas the birds on the left are not all the same. These lizards are all the same as each other, and they fit together to tile the plane. And there's rotational symmetry there. So you could turn it through 120 degrees about a carefully chosen point, and one lizard would take the position of the next one round. And if you did that 3 times, they get back to where they started.
So 120 degrees is 1/3 of a full rotation.
So red, the red lizard goes to the white one, the white or the yellow one. The yellow one goes to the green one, and the green one goes to the red one. When you do,
you can see how the 3 heads come together. The yellow, the green, and the red heads are literally formed together to make a little mini hexagon, and that's, you can see that there's 3 to make it all up, and then the tails kind of come, the back legs and the tails come together at the other end. Okay, I can see it. So there's 3 of them to make it. So yes, 1/3 is dividing 3/16 into thirds. Cool.
But then when you look at the bull's heads and the H there, you see there's a different sort of repeating pattern. Those patterns are repeated by just translation or shift.
Right, so you could do it like with a stamp, and you just keep moving it across the flat plane, and you could make it with a stamp, for example, because you can see that the bull's heads, if you rotate them, they're totally different upside down than they are the right way up. So you couldn't rotate the heads and match them, but you can stamp them and keep making copies of itself, and they will fit together that way.
but they fill the
Okay.
whole plane. There aren't any spaces or gaps between them.
Right.
So
yeah.
that's a tiling. Okay, so
Well, that's kind of a fun project in itself. That's doodling, isn't it?
absolutely,
If you
yes.
find a shape.
Great fun to find different tessellations, different tilings with different shapes.
Yeah.
Now, polyominoes are a very simple sort of a shape made up of squares, and here are some examples. There's a domino, you know, the game dominoes. Those are 2 squares.
Okay, so domino literally means 2 squares. Is that what it means?
Yes.
Okay, that's cool. I didn't know that.
And there's a triomino, 3 squares.
Yeah, that makes a more complicated game.
And there's a tetromino.
Okay, so triomino would be 3 squares and tetromino would be 4 squares.
Yes. And
so
then,
I got it. Wait. Pentomino is 5 squares.
Right. Okay. And
I kind of knew that. Sorry, guys. I knew that, but never thought about a hexomino before until Toni was preparing.
But you see,
this.
that's just one example, because you can arrange. You see, there's only one way to make a domino, but a triomino can be a strip of 3 in a line, or that L shape like that.
Right. Okay.
But so these are just one version, one example.
Okay, so the domino can only be 2 alongside each other. There's no other way of doing it. A triomino, you've either got the L shape or 3 in a line, and I can't think of any other way of doing it. The tetromino, you can do a couple more ways. You can make a tetromino a square, or a T shape, a T, or an L, or a whole line. So that's a square, a T shape, an L, a straight line. Oh, could it be ziggy-zaggy as well? Oh, it's the game Tetris, isn't it? It's all the possible shapes in the game, in the Tetris game.
Yes. So now look at the tessellation of H shapes. They're septominos. Can you count 7 squares there?
Okay, so each vertical part of the H can be made with 3, and so that's 6 on the left and right, and then in the center you've got 1 more to join them, so that's 7. Heptomino meaning 7, septomino, heptomino meaning 7.
Now the table here shows the number of possible shapes, polyominoes, and for example the hexomino, there are 35.
Did we find all the tetrominos? We had the square, the L, the T, the straight line, and the zigzag. Yeah, we found all the tetrominos.
Now the others, well, we'll challenge you. Can you find the other? Can you find all the pentominos? There are 12 of them. Okay. And by at the end of this hour, we'll give you the solution to that.
All right. So I might be doodling on this one as well, Toni. While we're at it, I might be searching for all the pentominos. But I'm actually, you've got to really watch out that you aren't repeating the same one that's just rotated a different way. I got caught out with that another time, didn't I? And plus I wasn't looking for the symmetry. We're not worried about symmetry with this one.
Now, we owe the name Reptile to these 2 men, really. It was coined by Solomon Goulom, who was a mathematician, but he also did quite a lot of serious maths and quite a lot of recreational maths. So he invented a lot of games and puzzles too. And Martin Gardner, who wrote extensively, and a lot of you will have seen his articles and books. So
actually, Toni, it's part of Maths Week Ireland. Usually on the last Sunday of Maths Week Ireland, so it will be a week yesterday, sorry. We gather for Gardner at the what's the park with the trees?
Anyway, you gather at the park and you play games.
Well, no, it's not just any park. It's the one with all the botanic gardens in Dublin. The Botanic Gardens in Dublin. So that's something. There's probably might be something going on this Sunday. So double check on the website if you can be in Dublin on Sunday.
So here we see a tetromino, an L shape, and you can see how 4 of them are put together to make a bigger tile, but the same shape. And then 4 more are put together to make an even bigger shape. And then you can see a floor tiled with the same shape. And
So-
that's your reptile.
So do all ominos make reptiles?
Good question. You can have a go. Everybody who's listening and sees this later can have a go at finding out the answer for themselves.
The dominoes makes a very, very simple one. Use
Yes.
4.
Yes.
Yeah, I think it's 4. Use 4, and you can just repeat that one. So
Yeah.
it's a
So
no, what was it?
So
what
you
did
may
you call
have
it when it's made up of 4?
a tetromino.
I mean, when you have a reptile made up with 4. It's okay. You used it earlier when it was a reptile made up with 4. 1, 2, 3,
So
4.
here we have the same tiling as you saw on the previous slide. And here what we're doing is showing, as it were, 6 stages. We label them 0, which is stage 0 is just a single L-shape triomino. Okay. Now, if you put 4 of them together inside it, you get what we call a stage 1. And then inside each of those, you put 4, you get stage 2. Now we go down to the lower one on the left. That's a stage 3. And on the bottom row, you've got stage 3, 4, and 5, and they become more colorful. And you could go on with that process forever. And this,
it's just repeating the same thing and you're adding another color basically for effect each time you go, go down another level, and it becomes really, really pretty, doesn't it?
And
that would be such a fun project to do. They do the colouring in project. This is a much more cerebral way of doing colouring in. You're actually doing something.
But whereas in your mathematical imagination, you can go on doing this forever. In practice, it gets too small for you to do it in more detail, which is interesting, isn't it? It's
that's where the engineer's mind comes. The mathematician can go on into infinity. The engineer will go, that's close enough. We can't practically do any more than that. So that's, I always praise the kids when they come up with comments like that. Right, that's the engineer speaking. You keep that up. That's good work. Now we're going to be mathematicians and imagine infinity.
The wonderful thing is in mathematics, in your mind, you can go to infinity, and it's sort of real in the mathematical world. Well, very real. And
it is
realizable.
It's real in your head.
Realizable.
It is realizable using mathematics.
Exactly. So what you've got here is a fractal process. None of these is a fractal. You have to actually go on forever to make the fractal. We in our sort of casual conversation, we might refer to something as a fractal, when we actually mean it's just quite a few stages of the fractal. So watch this.
Right. So we see fractals, but a real fractal goes on forever, basically.
Well, this is a fractal process.
Okay.
So that's...
Okay, and we've got 1, 2, 3, 4, 5, 6, 7, just 7 stages, and it would go on a lot more than that. But it's fascinating watching it.
Isn't it?
It's mesmerizing. You just sit here and
here's another one. Now this is the same tile, but it's making a completely different fractal. It's going white too, which is interesting.
Got a question. What is a mathematical imagination, Toni? It's a genuine question. What is I think it's a young person asking, Toni, and the question is, what is?
Well, I'm serious.
No, I know, but the question is, what is a mathematical imagination?
The answer is, it's what you see in your mind and what makes sense to you mathematically in your mind. And it's a very good example with these fractals that you can imagine the process going on forever. But if you actually try to draw it, they get too small for you to draw.
And the only way you can then continue the process is in your mind.
Yes, that's right. But you can realize it in your mind. So we can,
yeah, you can. It's kind of therapeutic. You can just sit somewhere with your eyes closed and just continue the process and just keep imagining it.
Yes.
In
Now,
a way like
here's a
software.
Here's a question. Why does this one go white? And now here's an answer. It's mixing colors. So it's to do with what we've just mentioned, and that is that the colors, you get more and more colors in there, and so your eye can't detect the difference. You can see the red, blue, and yellow at this stage, and still see the red, blue, and yellow. But as we get more and more copies, so they merge and appear white. So this is a third fractal, again made with this triomino, and it goes white because the colors are mixed. Now,
we're using light as well with this. It's using the pixels on a computer, using light, and the presence of all colors in light gives you white, gives you complete brightness, just like the sun, and or similar to the sun. And whereas if you're painting, it's the absence of all colors gives you white. So that's a little thing. Now, Jason is asking, how do you imagine it? It's a genuine question, and he's asking, say, please answer, how do you imagine it? Maybe
you think hard about it, and
you start with something that you can imagine. You start simple, don't you, Toni?
Yes.
So Jason is saying, I don't understand. How do you imagine it? I'm really confused. So we've got to start super simple. You've got to start with something you can imagine, something you can see.
Watch this pattern here. Now you can imagine how those pieces are fitted at each stage. You can imagine that going on. What we're doing is putting one of each sort. One of each sort together, like you see them, and you can still see them, and even at this stage you can see them, and then you have to imagine that they, and how you imagine it is you see what we're looking at now, and it's possible in theory. Imagine looking at it with a microscope. You'd see it still if you were looking at it with a microscope, because it would carry on getting smaller and smaller. And with a very powerful microscope, you can see a lot more than you can see with your eye.
So that's an idea. Yes, start simple. Start with something you can actually physically see, and then close your eyes and imagine it with your imagination, and then imagine what you'd see with a microscope. So take it a little step at a time, so you're not leaping from something you can imagine or even see to something you can't imagine. Just take it one step at a time, so that your brain basically expands, as it were. Your power of visualization expands with it. And also you have to practice visualizing, something you have to practice doing. So if this is a leap too far, and start with something a lot simpler and build up to something more complicated.
Now look at this beautiful rainbow circle here, okay? And look at these three colors, the red, blue, and yellow. Now, if you try this with paints, you'll find that if you mix yellow and red, they make an orange. And if you have equal quantities, you get a sort of intense orange. But if you put more yellow in and less red, you get a sort of a yellower, paler orange. And if you put more red and less yellow, it becomes more and more red and intense a color. Similarly, if you mix blue and yellow, you get green. And if you mix red and blue, you get purple. And as you look around the outer ring there, what you'll see, look at the red now and go round the ring, around it anti-clockwise. You've got red, orange, yellow, green, blue, indigo, and violet. You've got all the colors of the rainbow. I just love that. I think it's such a clever picture.
I agree. It's lovely, and it starts with the primary colors in the middle. It's another mesmerizing picture. And I think this Johannes Itten was nice and had a beautiful vision to create that. Jason says thank you, by the way. He says that helped. Thank you.
Good. Yes, it's quite an abstract idea and not particularly easy to imagine these infinite processes, but it's very important in mathematics, because in higher mathematics there's a lot of infinite processes. Now here's another iteration with this triomino tile, and look, I don't know whether you've seen the Sipinski triangle. This is a speciality of yours, isn't it, Caroline? Sipinski Triangle.
Yes, if anyone's watching that normally comes to Belfast, to Maths in the City in Belfast, they will have helped us make one of these. We've done it every single year in Belfast.
Well, this is
not true. We didn't do it in 2019, but every other year we've made a huge one in
Belfast. What you're talking about, Caroline, is a three-dimensional tetrahedron. This shape is only in 2 dimensions. What you're seeing now.
So so they call it a Sipinski gasket or a Sipinski triangle in 2 dimensions. You just make it with triangles then.
You can.
This is
not. Go on.
No, you're making this with the triominoes. It's not even.
Which is very surprising.
It's a surprise. It's a complete. I just realised. It just clicked. I mean, I know I saw this when we were doing the rehearsal, but it's like no. But all of this is just like a block with a bit sticking out, and you keep iterating and going through going smaller and smaller, and you end up with a fractal, a Sipinski triangle. It's fascinating.
Yes, and again you've got small areas of the primary colours, very few pixels on the screen, and finally the eye sees white because it can only detect a mix of the 3 colours. I think that's wonderful, and it's such a surprise because you can see the edges of this shape looking more and more straight, although they're not actually perfectly straight. There's still this zigzag even as it goes on, but with tiny, 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 tiny zigzags. Okay.
It's brilliant.
Now, let's see. So you asked a question earlier about which polyominoes would be reptiles. And here you see these 2 are. That's a tetromino and a pentomino, just one example. And you can see how each of them has got 4 smaller shapes inside it. And here's all right. So these are, again, rep4s. And of course, you can repeat this again and again infinitely often to produce a fractal. There's just 2 examples there. So we haven't said that every polyomino is a reptile, but certainly some of them are.
Right, and that's a challenge to find out which ones are polyominoes. I've been working towards making the 12 polyominoes. I knew there were 12, I have to say. I did know there were 12. So far, I've managed to find 2, 4, 5, 6, 7, 8, 9, 10, 11. I've got 1 more to find.
These are pentominoes made with 5 squares.
That's what I'm talking about.
There's one of them.
Right.
There's one of them.
Check.
There's another. There's a third. Caroline will show you.
Got that one. I do have them under. Well, right. Shall we do that now?
You're going to show us, Caroline.
Do you want me to do that now?
Yes.
Right. Let me remove that.
Just the 3.
Just those 3. Right. Let me put those on. Show. Oh dear. I've got it there. Just those 3.
We're still leaving it as a challenge for everybody to try it for themselves.
Like so. Right, there's the challenge. I'll remove all the others from the picture. I do have them under there, but I was looking to find all 12 of them without help now. Let's show you.
Can we see your visualizer?
Not yet. We're working on it. And hey,
there
presto.
You go. Now those are separate pieces, aren't they, Caroline? Those pieces.
Yes, these are. There's the L. There's what I call a zigzag or a piece of lightning, and there's that block that we know. So this is a poly. Oh, I don't know if that's
pentomino.
This one. No, that's not the word I was looking for. It was the reptile. Are they reptiles? This one is a reptile. It's one you just showed us. There. So that's 3 of them.
Yes. And you can make 12 of them, all different shapes, made with 5 squares, and you can fit them together to make a rectangle.
Right, so it's not just finding all of the pentominoes, it's actually fitting them. And what are the dimensions of this rectangle?
That's an interesting thought.
So
there's going to be 60 little 12. There's going to be 60 little squares, because there's 12 of them with 5 small squares, so that makes 5 12s are 60 little squares inside this rectangle. So it could be, well, it could be 3 by 20, but we can, and we're telling you that it starts with that in one corner, so it's at least 4 by something.
It could be 5. Oh, this is one end, is it? It's a complete end.
This is one corner.
Okay, so it's not a 5 by. So it's not a 5 by 12. So if this is 4, it's going to be 4 by. Well, I'll let you guys work out what it is.
It could be 4 by 15, couldn't it?
Could be.
But there's other possibilities too, and we're going to leave you to explore the other possibilities and to find the rectangle.
Okay.
Now let's look at these trapezia. These are all rep 4s.
Okay, hold on. When you're not can't be seen yet. And go.
Can you imagine now? Think about it. How you would fit 4 smaller copies of each of those trapezia into the outlines you see.
Wait. So you're saying these are reptiles. So we want to make, those are both trapezia. One's regular and one's not. One's symmetrical and one's not.
They're not regular.
And what you're saying, so I mean, I corrected myself, Toni. I said symmetrical. Yeah. One is. So you're going to make 4 smaller copies and make that same shape out of 4 smaller copies, just like all the other reptiles we've seen so far. Okay, that's a nice challenge to actually, and you'd have to work out. So what are the dimensions? Is it the edge length half? What's the scale of them?
I'm going to make it easier for you actually to do this, and that is to take one, right? Copy it 3 times, so you've got 4 copies, and then make a bigger one. It's easier to do that than to draw the smaller ones inside.
Right. Now, this is where, Jason, this is where you can use your imagination to imagine, if you take 4 of one of those, can you imagine how taking 4 of those rather than fitting them in the middle, Toni's saying it's easier to take 4 and make a bigger one. Using your imagination to do that might be a good start for using your imagination to imagine things going to infinity. It's called visualization.
There they are. There's a solution. Did you work it out?
I have to say, the one on the left, I did not. The one on the right, I was on my way to that.
But although if you get 4 copies that are all the same shape, although it's only the jigsaw, as it were, has only got 4 pieces, it's quite a challenge to put them together so you make a bigger copy, an enlargement of the shape. And Caroline,
go on.
Caroline asked about the scale factors. Well, the edge lengths are doubled, so linear scale factor is 2. And what about the areas?
You kind of have a clue with the area, don't you?
Yes.
Jason's really enjoying this. He says it's so interesting. Thank you, Jason.
Good.
So what is the area? Can someone put in the comments what they think? So the
area scale factor.
So the edge length scale factor is 2. What is the area scale factor? How much bigger is the area than the original, the one of those pieces?
Well, look at the lower copy, look at the lower version, and there you can see that when you take the smaller one, the smallest, or one of those 4, and then you look at the 4 put together, you've increased the edge length by doubling it, and you increase the area 4 times. So the area scale factor is 4.
You can just get it just by counting them, can't you, really, on this one?
Yeah.
Except for the fact that these are not to scale. So in theory, the bottom one is made up by 4 copies of the top one, but the top one's been shrunk. So it's,
well,
they're
yes,
not to scale.
you can be flexible there. You can imagine shrinking it and putting the copies inside itself, but you can also grow outwards, going bigger and bigger with enlargement, and you get shrink inwards.
A perfect time to use that imagination, Jason. Oh,
there's another trapezium, a different shape trapezium with a different tessellation.
It's subtly different.
It is.
But it is different.
It's quite like the one on the left in this, there's 2 right angles. But as you see, the way in which the pieces fit together inside, the jigsaw, is different.
Yeah, the third right angle end, as it were, the third bit of what would be a rectangle is shorter, and it's different. The proportion's different. Interesting.
Now, here's some fun for you. These aren't all possible reptiles at all, but there's a lot of them here. And the colors show you how the smaller pieces are fitting inside the bigger version. Okay,
so this is just like a stage 1. It's just the basic reptile that's made one shape, made with however many of the same smaller shape. And we've got the Sphinx up there. I can see the Sphinx.
Well, the Sphinx, where's the Sphinx? Oh, he's at the top, the third one along at the top.
Yeah.
Yes. And you can see on the right 2 different ways in which the 4 tiles, the tetrahedrons, are fitted. Oh, the 3 tiles on the top right-hand corner, that tiling, which we saw earlier, that's repeated. And then to the left of that, there are tetrahedrons, or the 4 squares fitting together. There's lots of different.
We've got another question from Jason. Do you mean our favorite? The question is, what's your favorite shape, Toni? Do you want specifically the reptile, the favorite reptile shape? Let's go with reptile shape, because that's the topic of our today's Happy Maths. What's your favorite reptile shape, Toni?
Oh, I know which mine is. It's that fish, isn't he?
Oh, wow.
He is made up with right-angled triangles. Can you see?
No. I can see. Okay, I can see the right angle. I can see 1, 2, 3, 4. I can see 4
right-angled
triangles. But those are made up with something else.
Well, inside, they're sort of well, that's why the arrow is there, to point out that they sort of intersect. So they actually fill the space. So they genuinely make a tiling. They actually fill space without any gaps or overlapping. But you can see on the smaller versions, you've got green, red, yellow, and blue fish, right? And you have got 2, 4, 6.
I'm going to make it bigger again.
You've got 8. You see, you've got 8 fish.
2, 4, 6, 8. Yeah, there's 8 fish that are the same shape as the bigger fish. It's made up of 8 smaller fish that also make 4 right-angled triangles, and they're also isosceles triangles, aren't they? Jason says he likes that shape best too.
And yes,
Jason
and that's
that shape best.
That's a rep 8. There's a
rep. That was the word 8. I was asking for earlier, Toni. Rep 8. I was looking for the rep 3 was what we were looking for earlier. It's rep 8. So however many it's made up of, it's a rep that number. Okay,
there's another fish there. I rather like that fish. He's a symmetrical fish.
3, 4, 5, 6, 7, 8. That's made up of 9
fish. Small fish.
So they're similar. They're similar shapes. They're the same.
So we have got a rep 9, a rep 8. The 2 fish are a rep 8 and a rep 9.
Okay.
Now, can you see a rep 2 there?
Rep2. Oh, there's the Swedish flag near the top, centre near the top. There's a yellow and blue.
Not right at the top, but as Caroline says, near the top.
Yes. It's to below and to the right of the Sphinx.
And it's a right-angled triangle made up of two smaller copies of itself.
Made two smaller isosceles right-angled triangles.
Absolutely.
And it's so simple and so beautiful. I like the little squares at the bottom, the itty-bitty squares made up of lots of other itty-bitty squares.
And they're also overlapping. I mean, if you sort of you look at it in terms of the colours are telling you what's replicated. You've got two squares, well, four if you like, just connecting at the corners, but they all sort of fit in and interlock with each other.
They're part of the same shape. It's deliberate. They've got the shape is those four bigger squares.
Yes.
So lots of itty bitty squares, 16. And then they're supposed to, just like the fish that interlock over each other, those do as well. So is that the same for, in that case, there's two triangles. So if you start at the far right, you've got like a J shape, and then you've got a, what's the name of the one with the two parallel lines? We started with those.
Not sure which one you're talking about, Caroline.
Start at the far right at the bottom, you've got the J shape. And then to the left of that, you've got tell me the name of that. Starts with a T.
That's a trapezium if you're English.
Yes.
And a trapezoid, it's a trapezoid if you're American.
That shape is the name always is. And then to the left of that, there are two triangles made up of 8 triangles. Are they supposed to be together as well? They make up one shape?
I think they are, yes.
So you can, because you can imagine that you could keep interlocking that shape to itself, so interspersing them with each other to make. So that's
you can have endless fun with this.
You really could. I mean, this is a lovely challenge. You could decorate a whole room with this. With different shapes.
Now here's our fish that the symmetrical fish. Okay, you can see how 9 copies of the fish fit into the bigger fish, and each one is made of 3 equilateral triangles.
And this, is this also come from that same wiki?
Yes.
Wikipedia? I'm just going to put that link back on again. So if you want to see any of these animations, these are coming from here. I'll give you the link again on that one.
I think it helps to see these actually taking shape before your very eyes.
I think it really does. And that will, going back to the visualization question earlier, it does help. You start with this and then you can go into more detail and go into smaller.
Now the rocket here is not is not a GIF. It's just a still thing. But if once you've seen it, how they can be intersecting, you can see this rocket shape and how that's also formed of equilateral triangles, and how they're put together.
And the colours really help as well.
Now, if you've got spotty paper like that, it's easy to make the patterns yourself. That's called isometric paper. Now, can you spot the Rep2? I think we already mentioned this.
We've got
that's
one
the
Rep2. Is there any other Rep2
this is a Rep9. There are quite a lot of Rep9s.
Right.
And then the next question is, and we've already talked about this, so we won't dwell on it now, but this question here is, how would you classify the other reptiles here? And we've already talked about them quite a lot.
Right. Okay. Now we're going to send this PDF, aren't we, to to CalMars, to the team at CalMars.
So you'll have we'll have all these pictures, and then you can do your own variations of the patterns. And we challenge you to do that. And it would be really interesting if on the YouTube, where you will see the recording of this Happy Maths Hour, you like to comment and add some of your own designs and pictures that you've created.
That would be fantastic.
Wouldn't
and
it
also,
be
by the way,
great?
do remember, which I didn't say earlier, I was supposed to say at the beginning, is remember to register. If you haven't already registered for Maths Week Ireland, please register. I'm going to put the link up for that as well. Well, the link put it under the ticker tape. Right, Toni, what else have we got?
Well, now here it's a bit confusing. You have to just think carefully. There are actually 4 different patterns here on the one screen, and these are octominoes. Here, the green, each green.
Oh, so
shape
each green and red one
is made up of 8
little squares.
And the two octominoes are put together to make a 4x4 square. And then you can tile the plane with those 4x4 squares.
That's easy peasy lemon squeezy. I mean,
Isn't
you can
it?
tile the plane with the square totally easily. So it's a matter of finding all the octominoes. So I guess it has to be an octomino because 2 8s are 16. So it would have to be a square number of squares in order to use this method.
A square, yes.
Right.
So there's a challenge.
So it would be half the square number, 2 of half the square number to fit into the square.
Now, each square can be replaced by 4 smaller copies over and over again, infinitely often, to produce a fractal. So again, we've got more reptiles here, and this time octominoes. There's so many different possibilities here. You can have endless fun with it. Now here, here's our Sipinski triangle that we referred to earlier. But here, if you look at this, you can see how the triangle is made up of lots of smaller triangles. Caroline does this with balloons, don't you, Caroline? It's not a triangle, it's tetrahedra or triangle.
Well, we can make the shape with balloons, but it's not as fun because that would have to go flat on the floor. Balloons pop when they go on the floor. We build it up. We build every year in Ireland. We build when I'm there. We build one that's has an 8-meter edge length. It's about 7 meters high.
Huge.
So
it's
like 4 times the height of most humans, or fairly.
So here,
average size humans.
You can see that at each stage, 3 triangles make the bigger one, or inside the triangle, you can put 3 smaller ones to the same. Now watch, 1, 2, 3. So you can see the shape on the right. On the left, I've repeated it 3 times. I'll undo it, and I'll do it again. 1, 2, 3. And you can see how 3 copies make the next bigger one. And how you see lots of holes in it. And this is similar to what we saw happening with the L shape, which was quite surprising. Here it's happening with our triangle. Now, if we look at this, you'll see something similar with a square with, in fact, this is 8 squares inside a 3x3 with a black hole in the middle. And then you have that pattern repeated at smaller and smaller scales, and you get this Sipinski carpet. Similar to the one with triangles, but this is done with squares.
I'm shaking my head, but I'm shaking out of, I just can't watch these things enough. They're just fascinating.
Aren't they fun? Yes. And now here, you've got on the right, you've got something which is again fractal, and this is what's called a dragon curve, made up. And this.
Why is it called a curve? I mean, I can see it's curvy. Is there a particular reason for calling it a curve? Or is it just because it's curvy?
Interesting that. Yes.
Because it is curvy, isn't it? Maybe they just called it curve because it looks like a dragon and it's curved.
Yes, a lot of these fractals depend on the edge rather than what's inside them. Yeah, there's our dragon curve, made up of 4 smaller copies of itself. And you can imagine doing that at smaller and smaller scales, but you could also imagine doing it at bigger and bigger scales.
Now that is stretching me to actually imagine doing that, because that is a very complicated shape, and you've got to get each shape exactly the same, and that shape has to be a reptile, so it has to tessellate the plane when they're all put together. So that requires a lot of precision, doesn't it, to create that? I suppose a computer's a really good way of doing it.
Yes, and Jason asked a question about how you imagine this infinite process, the thing going on and on, repeating itself infinitely often. So with the Sipinski carpet, what you could do is you could get a large piece of squared paper, or stick several pieces together to get a bigger one, in such a way that where they're joined, you don't break the pattern. You continue making, the paper, the squares are the same size, are repeated across as your bigger piece of paper. And then draw the biggest square you possibly, 3 by 3 square that you possibly can on it, and make this Sipinski carpet for yourself. In other words, you could start by blocking out the middle and making sure that's black, okay?
Right.
And then you could block out the middle of each of the 8 squares around it and make sure they're black. And then you could block out the middle of each of the 8 squares in these 8 squares. So you've got, as you see it, you've got 8 squares inside the 3 by 3, which would have with a black hole in the middle.
The arm, yeah, with the black hole, yeah.
Yeah,
8 squares around the outside with always black in the center.
And you could put 8. You could actually physically make sure that, well, you could color it black if you like.
I was going to say you could color those the 8 squares around the outside. You could color them and then just fill in the black part.
Well, I'm suggesting you do it with the blacks, you see, and you're getting smaller and smaller blacks. Well, and then if you imagine you could color around the blacks.
The color part. Oh, so just do the black first, right? Just do the black. So if you could do it on squared paper then to help you with the guidelines.
And when you get
squared paper, and then just color in the blacks. Right. Keep going. Yeah.
When you get your smallest black square that you're making is the size of the squares on your squared paper, then you can make smaller squares inside that. But as Caroline the engineer says, physically you can't do that forever, although you could imagine having a microscope and seeing, or a magnifying glass first and then a microscope, and making it look bigger, so you could imagine putting the smaller black squares inside.
I can attest to the fact that it is a lot easier to imagine it once you've actually done a project like that, because you really get into your head and you really understand how it works, but you've just done it, and you've done it to that detail so many times, and then actually it can be hard to disengage your mind, to stop going through the process and iterating again and again and again. You think, oh, if only I could do another layer, and then I could do another one, and then I can imagine doing another one and another one. It actually really facilitates that imagining to infinity if you actually do several layers yourself. Now, the other thing about that one, Toni, is you've got to be very careful about how many squares you use, in terms of making sure that you end up with one of the squares being a center square.
And there's something called a von Koch curve that we make a poster with groups quite often. And you do that by having an equilateral triangle and sticking an equilateral triangle in the middle of each edge, and then a smaller
that's half the edge length. Each one is half.
A third of the length.
I beg your pardon. Yes, of course. Each
And
one's a third. The edge lengths are a third, and so you keep going down.
And then you keep doing that with smaller and smaller and smaller triangles, and then so you stick them on, and then you get a pencil and you draw a smaller one still, because it's at this stage it's too small to get a small triangle and stick it on. That would be too fiddly, but you can draw it with a pencil. But actually, what happens with this sort of process is that you don't want to keep on doing it because it just takes a long time, and you've got the idea, so you want to imagine it anyway.
Well, you can do it. It's a great class project.
You
Everyone,
could.
and that has been done. There was a Guinness World Record attempt. I don't remember if they got it or not, but Matt Parker actually had people sending in mats, they called it. Well, they are called that, aren't they? The Sipinski carpet. It's probably carpet. People from all over the world sent in bits. Oh, don't show the puzzle yet. Let me show the pieces.
Well, I put that slide up, Caroline, because I want you to switch to your visualizer and show it. Even if you've seen it once, you won't remember it, so it still won't have spoilt the puzzle for you. Caroline has got all these pieces, and she's going to try and put them together.
That's funny.
She's going to put them together, right?
That is very funny, Toni. Right, going to put them together. Right, so I had some already put together, but I do not know how to solve this. Okay, so
that's how we started before.
That's what we had before, and these are all the pieces. And there is one. Let me just show you this. This was me attempting to make all the, without seeing the puzzle. I've got all my ideas of all the unique pentominos, but I'm missing one, so I'll find out now which one I didn't get. I think it was this one actually that I didn't get. All right, now you've got to somehow put these together, and we don't know for sure what we've got. Now I can't turn it over. That would be nice, wouldn't it, if I could do that, but I can't. They've got to stay this way up.
While you're watching what Caroline's doing, I'll say that if you go to the Aiming High website, and we will give you the link for this, you will find that there is and we'll also send you the PDF of this PowerPoint presentation. So what you will get from the Aiming High website is you will get a lot of ideas about fractals and reptiles and polyaminos, and you'll get a guide where you'll be able to think of different ways that if you're a teacher, that you can work on this with young people. And you'll also get a copy of this pentomino puzzle and its solution, so that you can cut it up and make a puzzle from it. I think this is what Caroline has done here.
Well, I'm assuming it's 4 wide. I don't know if I'm going to solve it.
So Caroline isn't cheating and looking at the solution. She's genuinely working hard. But you've only got 2 minutes, Caroline.
What? Well, somebody's going to have to. Hopefully, I'm giving you the hunger to solve it, because I don't think I'm going to solve it in 2 minutes. That one can't go across. That's got to go lengthways. But if I make that lengthways there, that's not going to work. Maybe here.
Right.
Okay.
So because we've got less than 2 minutes now, I'm going to show you. Okay. So if Caroline shows...
Yes, hold on. I'm just going to add that to the stream and remove... I've got to remove mine.
And you'll see it's 5 by 12. No? Yes.
It is. It is 5 by 12. No. That was a red herring, Toni. You and...
Oh, no, I said it could be, it could be, it could be.
Okay. Right.
And so here's another. So that one that's a solution, and the one which you've got an arrow showing, that one we saw earlier, which is a reptile. So you can put copies of itself inside, and you can build outwards with copies again. Which ones here are reptiles and which are not? They're not all reptiles. So which of these pentominoes
the
are
L
reptiles?
shape, the L, the 4 and 1, is that a reptile? Because you could make a rectangle with that. You can make a 5x2 rectangle. No.
We'll let everybody think about that, because time is up. So what we're suggesting is that you create other reptile shapes, draw your own tilings. A simple one to try is a parallelogram. And which regular polygons are reptiles? A regular polygon is a polygon which has edges all the same length, angles all equal. And you can investigate polyominoes, as we've suggested, and discover which polyominoes are reptiles. Lots and lots and lots of investigations, patterns to make, and things to create. So it's 6 o'clock in England.
Well,
and in Ireland.
and in Ireland, Dublin time, Belfast time.
But we know we've got listeners in South Africa where it's not 6 o'clock, it's 7 o'clock.
It's 7 o'clock at the moment until next week.
It's time to say goodbye, everybody.
So I'm going to say thank you very much for everybody that participated and was watching. We had quite a few viewers, Toni, and thank you for coming. I look forward to seeing you all next year, please. I hope so. And do sign up to Maths Week, to register if you haven't already registered for Maths Week Ireland. And again, thank you to Sheila and Owen and all of the CalMaths Maths Week Ireland team and all the funders, Waterford Institute of Technology, for making all of this possible. Thank you so much. And we'll see. And please do join us on Happy Maths Hour every week from 5 till 6. And here on the Maths Toys YouTube channel, please subscribe and then you'll get notifications, and click the notification bell and you'll get notifications every time we come out live. Thank you very much.
And Caroline, we're going to do Happy Maths Hour again on Science Week Ireland, aren't we?
We are planning to. We haven't spoken to them. We're going to suggest it that we do. We've got a plan. We have a plan, and it will be grand.
We want to be invited.
We want to be invited to do Maths Week, Happy Maths Hour, Happy Maths and Science Hour for Science Ireland in November. Thank you very much, everybody. Have a wonderful evening.
Bye, everybody.
Bye-bye.